My name is Amijai. Up until about 4 or 5 months ago, I was a postdoc in the Baker Lab in Seattle. I recently moved to Lund here in Sweden to open my research lab and hopefully achieve some of the things that I'm going to show you today. Okay, so we have a problem. The problem on one side is really cool. So, you know, our phones, laptops, all the things that everyone really love in this conference. However, these things come with a cost. And the cost is across the chain. So it starts with the mining that can result in this horrible thing that we see here. This is, by the way, from Romania. Through the energy-intensive processes that we use to produce these gadgets. And then with our ability to recycle these electronics back into something useful. And the bad news is that we're not doing a very good job. So we are making 62 billion kilograms of e-waste per year. And we're recycling, well, we're kind of treating, I wouldn't call it proper recycling, less than a third of it even. So we're not doing very well. Now, if you thought plastics and microplastics and nanoplastics is bad, this is really bad. Plastics are inert, and this is why we use plastic bottles to drink water. If you will drink your battery, you will die. So we need to solve it somehow. Oops. Okay. Nature has provided us with a blueprint, perhaps, on how we can do that. And I'm just going to show a few. It's really strange. Okay, so you do see the whole. Okay, I see half a screen. Okay, so so nature provided us with a blueprint of how to work out with inorganic, how to build nanostructures. And we kind of know it intuitively because think about our bones, eggshells, seashells. All of these things are made by nature. So nature found a way to genetically encode materials in 3D. But maybe a little bit less familiar is that this is also done in a nanoscale and even in a very interesting way functionally. So here you see a 2D array, which then extend to 3D array. You can see the sizes here. So this is better than what we can do today in lithography. This is done by silica sponges in the sea. So between these protein hexagons, you see silica. Here you see the giant clam. The giant clam is an endosymbiotic creature, which means that it's kind of having a relationship with an algae. To survive, and it organizes the algae in these columns near to light reflectors. And what is so unique about it is this light reflectors basically increases the quantum yield of this giant clam to about 60%. Just for reference, your plant atom is doing barely 2% quantum yield. So by organizing crystals in the nanoscales and microscales, these giant clams manage to outperform all our plants in our garden. And here you see a small bacteria. So you can see again the scale here, it's 200 nanometers. Yeah, so the whole thing here will go on, the whole thing from side to side will go maybe, say, 100 times into one of your hairs. And these bacteria are generating these nanocampuses. So each one of these is a magnet, which the bacteria evolved to form these campuses, and it uses it to position itself in the water column. This protein iron complexes exist even in our body. They store iron, so this is why this region is dark, because it's blocking the electron, and around them you see the proteins. And I don't need to tell you about beautiful seashells that we can find in the sea. And there are many more examples. So maybe we can use nature as a blueprint to solve our problems of making electronics and these cool devices in a more sustainable way. Now, what I didn't tell you is that a lot of these structures are basically built by these, let's call them nanomachines, that we all call proteins. Most of you know proteins as probably food, but they are much more complex than this. So here is a kind of a picture. I stole this from my boss' Nobel Prize lecture slide. So these are kind of illustration of all the different proteins that run our cells in our body, and you can see some of them forming these fibers, some of them enzyme, all kind of machinery which basically run on life. So within the last 4 billion years, nature evolved proteins to solve a lot of problems. Just think about all the things your body can do, but also think about, I don't know, your dog, your plant, so many things, and all these activities are mediated by proteins. So nature found this ultimate formula to make nanomachines that solve potentially every problem. So maybe we can now use more advanced method to solve our problems, which is to design protein that will organize semiconductors for us. Right. So what do we do? How do we do that? And how do we approach this problem in my lab? So, we're not going to make a plane. We didn't take 200 birds, tied them with a rope, and created a plane. What we did is we understood how a bird works, and then we applied it to build a plane. In a similar way, we applied this logic to designing protein. So we now understand, or more correctly now a certain model in our computer understands the principles that make a good protein. So we can design a computational pipeline going through a number of processes and end up with a protein that will solve our problem. And it all starts with models that create what we call a backbone, which will kind of give us a shape of this nanomachine. This is done, for example, in here with RF diffusion. There are other models using other techniques, but the reason why I like diffusion is because for people that are a bit familiar with artificial intelligence, for them understanding diffusion is kind of maybe more intuitive. So basically, you like a picture, that you do diffusion of pictures, you start with a lot of structures, you introduce noise to them in many, many steps until you get to complete noise. And you use this data set to then train the model to do the reverse action. So you start with complete noise and you create something that the model thinks is a good protein. If you then apply some confinement to the model, a restriction, you can make this protein do a function you want. Then once we have this shape, we use another model that knows to create a sequence. So basically, a protein is just a long chain that's kind of auto-fold into the shape. So the second model is kind of saying, well, given this shape, what will be the sequence that will result in the shape? And then we get this sequence. And then this sequence, we can predict it with another model, which is acting like an oracle and give us a prediction that the sequence we got from the second model is actually creating something we want. So this is not an API thing. This is not like ChatGPT. We work a lot with models that sit on the Linux servers, and you don't get a successful protein with one shot. You run thousands, if not millions, of instances to get to something that works. So there is a lot of filters in the middle that we customize to make this process work. But that doesn't end there. So once you have a sequence that makes the proteins that you want, you can now go on the computer and say, I want the DNA for it. And then someone sends you in a post DNA. You mix the DNA with bacteria. So the bacteria playing the trees here, they get the DNA and then they produce the proteins. So this is how we just do proteins, right? But we want to do a little bit more. We want to go through this chain of like buying a DNA and then creating protein, but we want to create materials from there that will look like something useful. A nanowire, a 2D surface that is highly structured in nanoscale. So can we do that? Can we move from the picture of here on the left to this, to something more biological to produce our semiconductors? So here is the things we need to solve to do that. First of all, we need to design something that will make the ions come from the solution and make the material. The problem is that if you just take a lot of material and you put it in water or in other solution, you will end up with just a lot of non-structured material. So you want the material to form only in the place that you define by the protein. Then you want the reversing, which you don't want it to form in other places where you have proteins, but you don't want the material to form. Then you want to control the entry of the material. You want maybe to catalyze something, so to change let's call it the condition very locally. And then you want to define all of this in architecture. And finally, you need to do it inside the living organism. So let's go step by step. So here is a template. What is a template? A template is basically solving a problem that materials in a solution are basically starting as ions. So, you take salt, you put it into water, and you just have ions in the salt. And then if you wait a bit, you kind of forming very small crystals. But the problem a lot of times is that because these crystals are not very favorable, they will go back to ions, and then you're kind of stuck with a cycle. And you're not forming what you want, which is kind of the material that you want to make. But if you have now a protein that interact with these small nuclei, the material will grow and shape into the structure you want. Right, so in our lab and before that, we come with a certain assumption of what will work to do this. And because we work computationally, we can start with completely random assumption, like we can say, okay, we need some sort of a charge difference, or we need to kind of grab the ions one by one, and then we can test them computationally. So the way we deal with it is that we first come with a lot of shapes that we want. So we just say, okay, we want shapes in different kind of periodicity and like maybe parallel and anti-parallel, and you can see there's different, some curvature. We don't know which one will work best, but we can collect all these shapes and then we can diversify them chemically. So basically proteins are composed from different building blocks, and we can use these building blocks to diversify the chemistry of those shapes. And basically then we can use all kind of instruments to express these proteins on small organisms called yeast, which we use to make beer. You all know them. And then we kind of select for one that seems to bind the nanoparticles that we are in, or the materials that we're interested to work with. And you can see as let's say the signal here is going up, it means that it's interacting better with the nanoparticles. So you can see before we sorted and after a lot of sorting, we got things that look better. Again, to the right here are things that are interacting with the material better. So we managed to first create a big library. There were 35,000 designs in this library, and then to zoom on a few. So this is how they look like. So out of this whole library, we got these designs for zinc oxide, which is a semiconductor, and these designs for hematite, which is a photocatalyst that can break water into hydrogen and oxygen with many applications. So can we use these to form the material? I will kind of skip two because I think one illustrates a point good enough. So the advantage of zinc oxide is because it's a semiconductor. When it forms, it has a property called fluorescence, which or photoluminescence in the case of zinc oxide. And what it means is that we can detect when it's forming. So imagine that I have like a tube with my zinc ions in it. I will only see the light, this light emerging when these ions are forming the nanoparticles. So you can see here what happens when we don't have the protein. We have a straight line. This is when we add a commercial template, which is basically the nanoparticles themselves. So this is what we call positive control. And this is when we add the protein, we get these increase. So our proteins manage to trigger the formation of the material specifically on them, the semiconductor material. And this is just confirmation using XRD that this forms the right material and not something else. Right, so here comes the cool part. So, okay, wow, we are able to make a small protein and put it into some tube. This is not very useful. We're not going to make GPUs from it. We need to start to structure this material. And the advantage of protein design is once we identify a motif that is doing the job. So let's say, for example, this one, we can now integrate it into this symmetric oligomers. So these are just designed to assemble by themselves. So when you mix them, when you kind of express them and you mix them, they form these shapes. So you can make what we call a C3. It's a cyclic symmetry where you kind of just turn the proteins 120 degrees. So you have like one unit, second unit, third unit, and the template or what we designed is inside. You can make the same with C6. You can make these small tubes that are reminding something that looks a bit more maybe like a transistor. Or you can make even a whole cage. And these are, here you have the designs, but here you have experimental evidence. So this is electron microscopy, and you can see that the shapes that came out are exactly the designs. And this is cryomicroscopy, so you can see here empty cages. You can see here cages that grew this black thing here, which is the zinc oxide. You can see also that we're still not controlling it absolutely, because we have some things that are forming these butterflies. But when we look and we refine the data, we find that the region that constitutes a major concentration of zinc oxides is exactly when where we plan it in here. And we can even see the ordering of the ions in the lattice. So we manage basically to find something that lowers the energy for the material to form and then to place it within kind of geometry that confine it to a shape. Oops. No, I don't want this. I want this. Right, I just want to mention another thing, that in order to move forward with this, we are trying now to create something that is completely fine. Remember these butterflies. This is not really something that's not something very useful when you have this. So we want things to be completely confined. So now in the lab, that's one Joe is working on it. We're building these pores that are able to kind of decide what is going in and what is going out. So kind of we're going to create these completely confined area was material we created, the semiconductor, is now completely isolated from the environment and also is not going to be contaminated by stuff. Right. Where are we going with this? Oops, jumping. So, okay, I showed you what I did basically almost until a few months ago, but we need to take it to something more useful. And the nice thing is that we now have more models that we can work with. We can work with, for example, reinforcement learning. So we have now parametric models that we're able to tell the model, okay, we want to have a helix. We want it left hand or right hand. The tube size radius is like this. The pitch is so-and-so. The helical radius is so-and-so. And then the model can generate a shape for us that will contain this volume inside. We can also provide the model with things that we force it to interact with. So we can take motifs that interact, for example, as this is with copper, and put it in exactly in the side. This is just a script that position it in the helical structure that we want. So then the model has both parametric restriction. You can give it a voxel map. And then also sites that you know that will do the job of creating the metal inside. So the idea here, hopefully will be achieved in the next 4 years, is to create these helical structures that have interesting conductivity and interesting optical properties, stuff that you can do with this. So first of all, if you move electron in this kind of fiber, and we're talking here on nanometer size, so this is really tiny, you can see the atoms arranged. So if you move electrons in this kind of wires, you get interesting phenomena like spin selectivity and so on, which are useful in electronics. You can also get very interesting optical properties. So, for example, this is one thing we're going to do. Another thing you can do is to say, okay, we know to do now a cage, let's say for zinc oxide, and another one maybe for another semiconductor, and another one we will maybe keep empty. So why don't we arrange it in optical patterns that we know are useful as kind of metamaterials, 2D metamaterials, and generate optical properties. So what do you do there? You the same way we design this cage, you start with a cage, you confine it, you create adapters to it that will allow you to place it exactly in 2D space. You put your template inside the catalytic area, and then you also control the entry of stuff by designing these pores that I showed you before. That's just the flip side of it. And then once you have this, you can start running another model to try to place them in 2D space. So just imagine each one of these is one of our blocks, and then it's jumping. So then, based on this, the model can then design the adapters to arrange them exactly in the 2D conformations that we want. So we start with modulating the patterns. We know now in Lund to, given a certain optical properties that we want, to use a machine learning model to get the pattern that we actually need to achieve this. So once we have these patterns from the physicists, we can put it in here, design the block, and allow this 2D arrays to form and make our 2D arrays. And then you can do some kind of lab tricks where you take Teflon, you put you make holes in the Teflon, you put membranes, and you organize your blocks on something that will look like a breadboard. So then kind of you organize them exactly in the pattern you want. And hopefully this will make the optical properties that we want. Right, finally, because I was talking about GPUs, perhaps something that will allow us more quickly to make GPUs. Basically, you can design proteins to form these assemblies and then decide exactly how they will assemble, what will be the gaps between them, and so on. And this is real data. This is a design hexagonal array. So this is, if you remember the beginning, I'm jumping back to the beginning. This reminds very much this, right? So look at this, and that's nature. And now we can do this. So this is real picture. A friend of mine who designed this, and you can see the design. It's composed of basically a C6, a hexagon, and another interface here of a C3, and this is what is forming this. You can make them in all kind of sizes and control the size, which means that you control the periodicity of the holes. Okay, but these are just proteins. How are we going to use it to make GPU? So here is a protein from silica sponges. These are made from glass in the sea. We can borrow this active site from this protein. This active site is taking organosilica from the sea, water, and it's kind of polymerize it into chains of silica, basically glass. So if we kind of take this, bore it, and put it into our 2D array, we will be able to form glass exactly on top of the arrays. If you then organize it in a way that you will have silica forming in these areas, and you make these antennas to make hole, you create a pattern where your protein is acting as a cast that forms silica with exact hole in it. Now, this is very useful because in this way you can basically create a genetically encoded silica mask for lithography. And because of the resolution of protein, you can basically outperform, at least on paper, our current state-of-the-art in lithography, UV lithography, which is 100 nanometers. Yes, there are very big machines that are much more expensive, that are able to do things better than this, but these are very, very, very expensive. So our ambition is not to have a $2 billion machine to make chips, but have something very cheap using UV to make chips. So basically, if we can do 100 nanomolar, nanometer, by the way, they are making lines. So the way you do the 100 nanometers is you make first line this way, and then you kind of tilt it around or rotate it around, then you do the 100 nanometers, and then you get 100 nanometer features. But with these, you can potentially even get sub-nanometer resolution, which is more than 2 orders of magnitude improvement on current state of the art. I'm not saying we'll get there, but potentially we can, even if we get to 10 nanometer difference, which is kind of, I wouldn't say easy, but not too much of a moonshot. We can already improve on current technology. And the nice thing is that it's genetically modified, genetically encoded, which means that someone can just have a bacteria in his freezer. He's growing this bacteria, throwing the protein into a tube, and he gets a lithography mask, which is kind of an interesting concept. Right, I just wanted to say that for me, this is part of a larger vision, which I call kind of in bio. The idea is that we make all this e-waste that I started to talk about. We throw it into acid. We throw bacteria that called extremophores that can live in these acids. They know to extract the ions from our e-waste, so they will leach it naturally. This has actually been used today to experimentally in some lab, at least that I work with in Germany, to do that. But because we have the designs, they can now make something that is not just a pile of different metals that came from our e-waste, but something very defined that has a lot of value, which could then be assembled into good stuff. Up until a month ago, this was an ambitious vision that I just wanted to do. The good news is that we're now assembling a team across Europe, Germany, France, Denmark, and Sweden to basically do that. We have collaborators in Germany that they already work in mines in Germany to use bacteria to leach the iron. So we're going to design for them the protein to put in these bacteria that will sort the material. That will already be a big achievement, and then try to make directly from these mine waste and e-waste something useful. I just wanted to say that, okay, this is on Earth, but somehow I got a phone call from our team got kind of a discussion with ESA about using this in space. So on Earth, you can bring a big machine and harvest a mine, and it's hard to compete with the amount of metals and resources a big tractor can extract from the ground. And then you need to work really hard to make your stuff more valuable, and that's the idea of shaping them with protein. But on the moon, you cannot get tractors. So the idea of sending a small bacteria in a tiny tube to space and to the moon is attractive to ESA, and by the way, also to the American counterparts. And the idea will be to design everything for moon regolith. So we're already working with Luxembourg, that they have like the biggest space resources initiative in Europe, to try to identify interesting things in the moon regolith that we can target with our protein. So the idea is that we will not only use it on Earth, but maybe also to extract resources on the moon. And a funny anecdote on this is that on Earth, it's not a problem to buy bacteria food, but on the moon is a little bit of a problem, and the solution is basically astronaut outings. I didn't know this, but when you talk to people that deal with space, this is very expensive. Taking 1 kilo basically taking 1 kilo to lower Earth orbit is about $10,000. And if you're an astronaut in space, you eat per day, I don't know how much you eat per day, kilo, 2 kilo. Let's say half of it you take in, half of it is going out. So you're basically wasting $10,000 per day per astronaut. And that lower Earth orbit on the moon, it's much, much more expensive. So if we can use these outings as sources for our bacteria to grow and make our future solar cells on the moon, it will be amazing. I just thought it's very funny. And yeah, that's current team in Lund that are working to make this dream come true. This is us drinking a little bit of alcohol here and coffee in here, depend on the hour. And yeah, questions. And also, if you are interested in this in any way, feel free to either go to the website, saragovi.science, or email me. I'm happy to talk always about crazy stuff. And thank you for your attention. And I guess questions? Yes, I think we have a question here. Oh, okay. So basically, proteins have an angstrom resolution. We can move atom by atom, depends. So I cannot tell you if this will translate to the material being atom, but for example, we can dope something exactly where we want it in atomic resolution. So we have sub-nanometer resolution, at least with a protein. Some of it will translate to the material. I don't know if everything, yes.
What's the speed in which these proteins work? Like, how long does it take to build a feature?
Okay, so yeah, this question could be answered in two ways. First of all, what is the process of designing something like this? And second, once you design it, how long it will take? So the computational design depends on the difficulty of the problem. You can get a protein that bind a certain metal or antibiotic in 3 days. Making complex architecture will probably take a student at least a few months to design. And then you need to test it experimentally. So let's say within a few months, one student, so it's not Google or NVIDIA, will produce let's say a working prototype. Then once the protein are expressed in bacteria, which depends on how fast is the student in the lab, I mean, you can do it in 2-3 days. And then once you have the proteins, you just throw it into the solution, and that will happen pretty fast. I mean, that's a matter of minutes to make the material. The nice thing is once it's working, you have the code forever. It's not forever, but for a long time stored in the DNA. Yeah. Hopefully I answered your question. Yeah.
Is it possible to produce like other materials like silicon, germanium, or something close to pure silica or silicon?
Okay, so silica we do. Silicon is might be more difficult. So we are now looking at low-hanging fruits, which are semiconductors we can do inside nice watery conditions that we know that our protein likes. In principle, we can think about other ways to do it in a more hash environment, but we're now focused on things that are easy to do. I would say that anyway, there is a move to wide bandgap semiconductors because of all the car chargers. So anyway, the industry is moving away from silicon, to things like gallium oxide or all kind of new semiconductors, just because the silicon is not very robust for charging a battery fast, like your car battery. Yeah.
And the second question I have, is there any remaining part of this biomaterial left within the product?
Yeah, so it depends what you want to do. If you want to keep it, then you keep it. Sometimes it's useful. For example, when you want to do semiconductor-based detector for medical applications and so on. But you can also heat it to 300 degrees and then it's gone. Okay. So you can dry it, heat it, and then you have only the crystal. Yeah.
Okay. Thank you.
Any further questions?
So I guess it's biological, and it degrades. So you have to make new batches of these creators, and then or.
Yeah. So two things. So first of all, design protein are extremely robust. So, we all remember during COVID, everyone was talking about these antibodies sitting in -80 and how much it's expensive to keep them in -80. And in our labs, we keep the proteins on the table. We go on vacation. We don't care. They're fine. But eventually, like you said, they degrade. The nice thing is that you can produce more, and also this is completely recyclable. I mean, proteins are food, right? We eat them. So technically you can drink it. It's a protein drink.
Cool, thanks.
GMO, yes. Oh, another one, yes?
You said that your technology cannot compete against the industrial mining, for example, in extracting those materials. But if you once have the bacteria, then you can just reproduce it. I would imagine it is extremely cheap to use it for any application once you designed the bacteria. Isn't that the case? Well, why is it not feasible to?
In principle, you're right. If you had one bacteria and enough food, you could have covered on the Earth with this bacteria overnight. So in principle, on paper, you're right. It's just that industry has a mature thing. So I think this potentially, if this kind of become more applicable, it could be used for more and more application and replace the heavy machinery. But it's hard. What I meant is that it's hard to compete with them because the scales that they are working on is tons. It's not grams or kilo. Oops, sorry. So when we're talking to mining companies, they're like, so how many tons do you do per day? Yes, obviously we don't do tons right now, but potentially bacteria could be expanded to cover a whole mine and leach materials out.
Okay, but that was sort of the question. Why can't you scale it to get tons? So what's the problem in that?
You can potentially, there are some EU regulations, but you can potentially, it's just that we don't know it yet. For example, we need to work in a very acidic solution. We still don't understand the infrastructure. So, for example, when I work with the teams, across European teams, so, I bring the protein design, and then someone that engineers this extreme bacteria is going to, she will know how to put it in with the rocks inside the acid, and someone else will do the NMR to test it. To be able to scale it to tons, you need to understand how you're handling it. For e-waste, you can win. You can win because we don't know to recycle it. Yeah. Thank you.